everyone, so today I'm going to just solve the quiz question, which is about finding a linear regression model for the following data set. It's a small data set, and this is the dependent variable, as you can see here, and the rest are the independent variables. So we start our investigation, of course, with the data analysis 2-pack, regression, and then I'm going to select the label as well of the dependent variable. This should be checked. And similarly, checking and selecting the labels of the independent variables, as you can see here. And now I want the residuals, the residual plot, and hopefully we can get the output displayed nicely in the same sheet. So let's take a look. First thing first is to investigate the p-values of the independent variables. I'm gonna first of all make this in bold and start having a color, start to color those that satisfy the 0.05 threshold and those that don't. So in green, I can see that these variables, the p-value of these variables are less than 0.05, which is the alpha, the threshold. This variable unfortunately does not, it triples, so it is going to be highlighted in red, while the HRs and PBs are in green. All right. So now we have this variable that is insignificant. First thing first is we try to take a look if the residuals, a very major residual, is the reason for such a problem. So I'm going to take the two standard errors and I'm going to test here the presence of any outliers. So if this is less than or equal to the two standard errors, and let's put it in an absolute reference, give me 1, else give me 0, which is the undesirable situation where I have an outlier. Here I can see that I have an outlier at 8, and I also have an outlier here at 13, in fact, indeed. So it's a very difficult decision. So let me just to check the difference in the distance minus the two standard errors. So let's see the difference here. How far off are they? So this is about wait a minute, I'm sorry, I need to freeze that cell. Okay, so given that, and is this, everything is all right? Yeah, I think so. Okay, good. So over here, this difference is 14, while the difference here is 6. So I'm going to start with this first outlier over here, and I'm gonna investigate whether eliminating this outlier, which is record number 8, will make any difference. So let me just identify the here record number 8 is in fact maybe problematic for me. So let me first investigate what happens if I get rid of the outliers. These are not important as of now. Well, actually, yeah, they're not. So put it like that. And let me get rid of Milwaukee, which shown to be an outlier. And also try to run the regression analysis again. Hopefully, we will have the variable that was insignificant to be significant again. So here is the dependent variable. And let's feed into the independent variables without Milwaukee. And now let's see what happens. So here's the output right there. And here's the output. So we can see here that we have the p-value over here of singles is okay, okay, here is still not okay. So there is no improvement. So first step, this is the first step of the process of thought. First step is to investigate the model, the p-value of the variables. So we found out that this variable is problematic. So we said, okay, first thing first, let's see if the outliers are the reason for this problem. So we eliminated the highest outlier, but then we still found out that this has not made the model any better. For this purpose, we're gonna retreat, go back again to where we were over here, keep Milwaukee, okay? And then what we need to do is we need to drop the variable. So we investigated the outlier, and now we want to drop the variable. So basically we're gonna keep Milwaukee. I'm just gonna keep it, and then I'm gonna just to drop the triples. I think triples was the, yeah, it was problematic. So I'm gonna just get rid of triples, and now I'm gonna go to data and take the runs being the dependent variable. What am I doing here? Okay, again, I'm sorry. Here and here. Okay, and then labels, residuals, everything is nice. And let's have the output here, and okay, good. Let's take a look at the p-values. Here's the p-values. So over here, intercept, we don't take a look at it. These guys are all fine. How about here? Yes. And how about here? Okay, so seems like all the variables are rendered significant. They are all having a p-value, as you can see here. This is e to the minus 8, e to the minus 5, e to the minus 10, and this guy has many zeros before it. So it's 0.05. So all independent variables are significant, and given the linear regression model assumptions are validated. Okay, so let's now take a look at one of the questions is to investigate the goodness of fit. So let's do that. So we say this model explains about how much. It explains about the this much. Let's put it in percentage. 92% of variation in dependent variable, which is the runs. And then over here we need to find the how the residuals, if the residuals lie in within two standard errors, because we need the absolute error for visual depiction in case we want to test for heteroscedasticity. So I'm going to just get them done already, and then I will compute the two standard error over here and use this value to see if this value is less than this value, and let's freeze it over here. Give me 1, else give me 0. So over here we have 1, and then we need to sum. So we're gonna sum these guys, how many ones, and then divide over the count. So you will find out that we have some problems here, because 93% of the values are in within one standard error. So this is what you comment. You will find out that 93% of the values are in within two standard errors. For this purpose, I will back again decide to check if I get rid of this outlier will enhance my the 95%. So over here, guys, this is the data that we got without number 8. You see 7, 8. So I got rid of the outlier. So let's check. This is the ABS residual. So you see, guys, why you need to really investigate the outliers. Now we will see and check what happens to the standard errors, to the errors, when we get rid of a big outlier. So what did I do this for? So this is the two standard errors, and here, if this value of residual is less than or equal to this guy, it's in within two standard errors, then give me 1, else give me 0, and let's now find out how many in there. Sum, how many of these residuals lie in within over the count, the total. I don't really need to do count. I know that the number of so now I got 96%. So it is important and imperative that for a better goodness of fit that we carry on with the model without the outlier. So over here we're going to just go goodness of fit. If you continue with this model in the test, this kind of model, I will give you some points, but you need to be smart enough to understand that you need a very good fitness of fit, and for this purpose you really need to get a model that has here adjusted R squared, and over here is I have 96% of residuals lie within two standard errors. Okay, so now I'm gonna take this. But in fact, oh, sorry, but I'm sorry. This is the data set is okay, but it has this guy, this variable. So I need to, in fact, get this data set without point number 8, as you can see here, which was Milwaukee, I guess, and I'm gonna drop triples. Yeah, so let's do that and get rid of triples, and now we're gonna get hopefully good results on both fronts, basically on the goodness of fit as well as on the p-values of the independent variables. All right, very good, very good. Let's take a look, check the p-values most importantly for now. This is good, this is good, this is good, this is good. All of them pass. Good, very good. All right, now let's take a look at the standard error. So let's, again, need some patience. ABS of residuals. So ABS, and then let's do the test. 2 times standard errors, and now if this value lies within 2 standard errors, give me 1, else give me a 0, and we all know that this guy here should be absolute reference, like that. And now let's write something about the goodness of fit. Goodness of fit here, the model explains about how much adjusted R squared, this much of the variance in dependent variable, which is the number of runs. Now let's go ahead and do the computations. How many of these guys over the total number of observations is 27. So over here I have 96% of residuals lie within 2 standard errors. Now this significant F is also less than 0.05, so we reject the null hypothesis of no linearity. So all together, all independent variables, independent variables, oh man, independent variables construct a linear model to explain the variation in dependent variable. Okay, over here, yes, all these guys are less than 0.05, so all independent variables have a p-value that renders them significant. So all of them are significant given the linear regression assumptions are validated. Okay, so very good, very good. So here we have the two standard errors right there. Okay, oh sorry, I hit the save. Okay, so now let's check the normality assumptions. The first one, let's check the assumptions of the regression. The first one, in the quiz, I told you not to check the normality assumptions, and I told you the normality assumption is already being validated. But in fact, because we know where we got the data set, but in fact, if you check the normality assumption, you'll find out there is problems with normality assumption. But for the quiz purposes, I told you not to check it for a reason, because there is a problem, and I don't want you to. You see, you can tell that there's a problem with the skewness, and here's kurtosis. We have to change it. And the problem with the kurtosis, as you can see, guys, this is only 27 observations, like almost 30. So if we take a look at this table, we'll find out that there's huge problems with the normality assumption. However, I told you that this assumption is being validated so that you can just carry on with the data set as is. Now, what happens if you get rid of more outliers? This is a small data set. I don't think that there will be any improvement. So in the quiz, you don't need to take this as an output. You just need to carry on with heteroscedasticity test for the homoscedasticity assumption. First thing is the visual depiction. For visual depiction, we take the absolute residuals and we plot them here versus the predicted values. So the X series will be this predicted values as an output of the linear regression, and this would be called the heteroscedasticity or visual depiction of heteroscedasticity, if it is present or not. So over here we can see maybe we need to start the variables here, the axes here with probably 500 maybe, so that we can see, and then we can also add a trend line. It's linear. It will be fun to see. Seems like the linear line is really flat. It's not that strong correlation among both of them. But still, let's go ahead with doing or performing the Krush-Pagan test. And I have to say that this test, it in fact depends on one of its assumptions is the normality of the residuals. So this is, as I told you, not the bestest test ever. I mean, there's also other problems with this test, but it is good enough for us. It is a bit advanced for you guys as bachelor students, but it's good enough. Don't worry about it. There's other tests that doesn't necessarily rely on the normality assumption, but why wouldn't I get the normality assumption validated? If this normality assumption is not validated, I have every reason to doubt the reliability and feasibility of these p-values. But for the quiz purposes, I told you do not to check the normality assumption, assume that it's validated, it's all right, so that you can just perform the test, because I want to just make sure that you know how to perform the test. So over here for the Krush-Pagan test, we need the residuals square. So we're gonna take the square of these guys, the residuals, and then we take them as the dependent variable for a regression model. So this regression model will take the squares of the residuals, and as independent variable, it will take the independent variables, guys. We don't need these for this test, but let's line up the output right underneath the name of the test. And we have 27 observations, so n will be 27 multiplied by the R square of the test. And then for the p-value, we're gonna take this. I forgot about the degrees of freedom. Here we have 4 different variables. 1, 2, 3, 4. So we're gonna add 4 in there, and then we find out that over here the p-value is indeed greater than 0.05. So this means we have no, we failed to reject the null hypothesis of no heteroscedasticity. So we have no reason to doubt heteroscedasticity. Okay. Now the last assumption will be multi-collinearity. So for multi-collinearity, I really don't care if you want to plot the correlation table, because I would like you to get the VIF, but I asked in the quiz that you plot the correlation table, because I just want to make sure that you know how to do it. Oh, I just put it somewhere else. Okay. So the correlation, I would like the correlation table to be placed somewhere here. You can tell from the correlations that they are all very low, but just because I asked you for the VIF, I'm going to put here R square, I'm going to put here VIF, and now let's see how we get the VIF via Excel. Sorry, and keep on saving. So basically what we do is we take the independent variables right there, and then I'm gonna highlight singles in green, so this will be the dependent variable at one run. Then I'm gonna take the same data set and highlight this time the BBS in green, so this will be the dependent variable at this run. Then I'm gonna take the data set again. Not sure if I can, in fact, yeah, I need to highlight it again. I'm going to take the data set again. Let me just, I need to take it 2 more times, so I'm just gonna copy that 2 more times for now. Okay, so now I got singles and I got PPS. I want doubles to be the dependent variable because all the independent variables supposed to be lined up. I need to just shift that there. Over here, I'm going to take this guy to be the dependent variable. So I'm just going to take it and shift them over here. So now we are ready to perform our analysis or our regression model here. So let's go to data analysis, not correlation this time, regression. And I'm going to take singles as a dependent variable first time. Then X range would be these guys over here. Okay, labels are there. Output, I don't need the residuals, so I'm just going to put the output and line it up over here. So here's the first 4 singles. Now let's run the same regression analysis, but this time for this variable. Okay, and here's the output. And then again. Okay. So now we got the regression models done. Let's take the R-square for singles model, which is, I think, the first model that we've done. So R-square is this one. And then for BB, oh, wait a minute. So this is where the first output. Wait a minute, we are here. Okay, this output, I'm just going to delete it, it's in the end of nowhere. So now for doubles, yeah. So doubles is basically over here, R squared, not adjusted R squared. And then we need HRs, which is basically this one. And then we need the R square for the last one is BBs. Right? That was the last one, BBs. Yes. And now the VIF is basically 1 over 1 minus this R square. And here we go. The VIF here is all VIF measures are below 5. We have no severe multi-linearity detected in the data set. So basically, I keep on saving. So basically, these independent variables, as you can see, are not highly correlated. You know, guys, when I look at the residuals plots, this is why I told you that we assume also random distribution. When I look at the residuals plot, they look random to me, but that doesn't still mean that we can pass it as random distribution, normal distribution of the residuals, unless you are given so, you are told so in the quiz. So what are the process of thought? So the process of thought, again, in summary, was as follows. We have the data set. First thing we've done is we crunched the data. We got the model. Here, we got an insignificant variable. First thing first, we checked for outliers. We detected a very big outlier over here. So first of all, we deleted that big outlier, which was found to be Milwaukee point number 8. When we dropped the outlier, unfortunately, we still got triples as an insignificant variable. So we said, all right, we don't need to drop the outlier maybe. So we're just going to take the data set and drop instead triples, which was the insignificant variable. When we've done that, we ended up with, I think we've done it here. When we've done that, where did we run the analysis and then, here. When we dropped singles, we ended up with 93% only of the residuals lie in within 2 standard error. This means the goodness of fit isn't great. So the model isn't that awesome. So basically what you need to do is we need to get rid of that outlier. Maybe if we get rid of that outlier, which was point number 8 here, maybe this will improve. So if you guys haven't done so and continued with the investigation, I will give you points, of course, for that. But the ideal scenario, those who are those students who got rid of the outlier and then got a better model without the outlier and then proceeded as told. I told you that don't worry about the normality assumption, it will be validated. And you could also get the depiction, the visual depiction for heteroscedasticity, the Push-Pagan test, and then the multi-linearity. And this will be it. Now for those who decided to proceed here, so basically let's take a look at the normality check very quickly. You can see that the normality check is also invalidated. Why? Because basically you have the kurtosis being very high, 5.8. So also the normality assumption is not validated in their case, so it's almost the same. However, I think heteroscedasticity would be fine, I believe, and multi-linearity might be fine. I could check it with you right now, but I don't want the video to be elongated. However, if you got this and kept it as is, it's okay with me. You're just gonna lose a couple of points, not much. But the best scenario, here's the ideal solution right there, is to get rid of one outlier, get rid of one independent variable, so that you can get a better goodness of fit and you can get all the independent variables being significant. All right, guys, thank you so much for today, and I'll see you next semester.